Welcome to the Explainer. Have you ever thought about how chemists take a complete mess, a chemical soup really, and pull out one single pure thing from it? Well, today, that's exactly what we're going to do. We're following that journey from a messy mixture all the way to a perfectly identified compound. Let's get into it. Right, so this is the big question for any chemist who's trying to make something new. How do you get rid of all the junk? And then, how do you prove what you've actually made? It's a two-part problem, and today we're going to look at the super clever ways they solve it. So here's our game plan. We're going to follow the exact steps a real chemist would take. We'll start with the big cleanup job and end with the grand finale, finding out the compound's true identity. All right, let's dive in. First things first, we gotta ask, why are chemists so completely obsessed with getting things pure? I mean, why not just work with the messy stuff? What's the big deal? Well, here's the thing. Those little impurities, they can totally throw off your results. Just imagine you're testing a new medicine, but it's actually a tiny bit of leftover gunk that's causing all the side effects. See? To know what your compound really does, you have to get it all by itself. Okay, so how do chemists even start this cleanup? It's actually pretty cool. They start by using simple, basic physics. The whole first step is about sorting molecules based on their fundamental properties. Let's look at two of the most popular methods. For solids, you've got crystallization. If you've ever made sugar crystals at home, you've done this. Pure crystals form out of a solution, leaving the junk behind. And for liquids, there's distillation, which is all about one thing: boiling points. Let's zoom in on distillation for a second, because it's such an elegant idea. And it's used absolutely everywhere, from small labs to giant industrial factories. It's a real workhorse of chemistry. So it's a really simple four-step dance. You heat the mix, right? The liquid that boils more easily turns into a vapor first. That vapor travels up and into a cold tube where, poof, it turns back into a pure liquid. And you just collect it in a new flask. It's perfect for separating something like chloroform, which boils at a pretty low 334 Kelvin, from aniline, which won't boil until it hits a whopping 457 K. But what if your liquids have boiling points that are super close? Or what if your precious compound breaks down if you heat it too much? No worries, chemists have figured this out. For those tricky situations, like in the petroleum industry, they use something called fractional distillation. And for stuff that can't take the heat, they use steam distillation, which lets them do the job at a much lower, safer temperature. All right, now for the real heavy hitter of the purification world. This technique is so powerful, it can separate molecules that are almost identical. Let's talk about chromatography. And the name itself is a fantastic clue about where it came from. Chroma is Greek for color, and that's because it was first invented to separate the different colored bits, the pigments, in plant leaves. Pretty cool, huh? Of course, today we use it for all sorts of things, colorful or not. The whole idea is kind of like a race. You've got your stationary phase. Think of it like a sticky running track. Then you've got your mobile phase, which is a liquid that flows over the track, pushing the racers along. Now, some molecules in your mix are stickier, so they grab onto the track and move really slowly. The less sticky ones get washed along much faster, and that difference in speed is what separates everything out. Simple, but so powerful. Now, two of the most common types you'll see are column chromatography and thin layer chromatography, or just TLC. With column, the sticky track is packed inside a big glass tube, which is great when you need to separate a lot of stuff. TLC, on the other hand, uses just a thin little layer on a glass plate. It's perfect for doing a quick check to see, hey, is my sample pure yet? And, this process is so precise, we can actually put a number on it. It's called the RF value. It's just a simple ratio. How far did your spot travel compared to how far the liquid traveled? And here's the kicker. A pure compound will always have the same RF value if you do the experiment the same way. It's like a unique fingerprint for that molecule. Okay, big step. Our compound is pure. The cleanup is finally done. But what is it? What's it actually made of? Time to put on our detective hats because we're moving on to something called qualitative analysis. You see, almost every organic compound has carbon and hydrogen. That's kind of the default. But it's the other elements, the nitrogen, the sulfur, all that stuff, that really give a compound its special powers and personality. So we absolutely need a reliable way to check if they're in there. And for that, chemists have a classic trick up their sleeve, the Lassigne's test. It's a really smart procedure that takes those elements and turns them into simple ions that give you these beautiful telltale signs. You get this brilliant Prussian blue color, that's a dead giveaway for nitrogen. A black solid suddenly appears, you've got sulfur. It's like chemical forensics, uncovering clues. We're in the home stretch now. We know what elements are hiding in our pure compound. The very last step is to figure out exactly how much of each one is in there. This is what we call quantitative analysis. And this is the key difference, right? The last step, qualitative, told us, yep, there's nitrogen in here. But this step, quantitative, tells us there is exactly 17.46% nitrogen by mass. And getting that precise number, well, that's the key to unlocking the final formula. So, these classic techniques, you might hear names like the Dumas method or the Kaldal method, they're all designed for one thing, to give us those hard numbers. They let chemists measure the exact mass percentage of every single element in their nice, clean sample. And once you have those exact percentages, you can do the math to figure out the simplest ratio of atoms. That's called the empirical formula. And with just one more piece of info, the compound's total mass, you can find the molecular formula, the true identity of your molecule. And just like that, the entire puzzle is solved. You know, this whole journey from a messy mixture to a final, perfect formula, it isn't just some boring lab exercise. It is the absolute foundation of the modern world around us, from medicine to material science and everything in between. This process is essential. Thanks so much for joining this explainer.